So we have here with us today a notable researcher who has done a lot of outstanding work. He's a lecturer in the finance division of the School of Business, University of Leicester. He started his career as an actuarial mathematician, I will call it, and has his first degree in actuarial mathematics, statistics, and an MSc in mathematical statistics. So he's a mathematician, I would say. And he holds a PhD in statistical economics. And as a result, his research focus has been on asset pricing, financial economics, econometric theory, behavioral decision theory, and probability and stochastic process with applications to finance. He conducts his research on decision-making in the presence of risk and uncertainty. And so he has used micro foundation of financial economics, economic theory, statistical decision theory, and behavioral economics to construct empirical processes, to generate decision-making under risk and uncertainty. And in doing this, he has used tools from diverse branches of mathematics, especially given his background in mathematics. So, and he has used this to identify and model those processes from first principle. The approach has led to innovative research and produced many outstanding outputs. For example, his paper on risk torsion concepts was voted by Money Science as one of the top innovative papers. And his modified Sharpe ratio statistics for high-frequency traders performance evaluation was recommended even to practitioners. So it was awarded a Best Paper Prize at the International Risk Management Conference sponsored by the New York University and the EU Joint Research Center for its innovations in estimating risk attitude during unconventional monetary policy responses to rare disasters. His current research activities include the construction of a credit risk index with myopic loss aversion to credit default, perceptions of risk, penalized reference dependent utility functions, representation theory of risk attitude, econometric test for factor timing portfolios, machine learning with big data in finance. And he has also done some research on managerial compensation contracts in revolving doors between government and industry, large deviation probability estimates for irrational exuberance in behavioral dynamic system and financial market instability. He's the lead editor for Frontier in Applied Mathematics and Statistics, especially the Mathematical Finance special issue on machine learning and factor pricing in finance. He has also refereed top journals in mathematics, finance, and economics, and he has been invited to present his paper all over the world. He's a fellow of the Royal Statistical Society and also a fellow of the Higher Education Academy. I will invite you to join me in welcoming Charles-Cadogan to present his paper today to us. His paper is titled Quantitative Easing of Fear During Real Disaster, which is really his specialty. You are welcome, Charles. The floor, okay. I will invite you to the floor. The floor is yours.
Okay, I thank you for the wonderful introduction. I'm gonna have to kind of cut down on my bio. It's kind of a little long here, but yeah, let me get right into this paper. The motivation for this paper is, again, as you've alluded, I am interested in estimating risk attitudes, and one of the things that happened during the pandemic, as you know, a lot of research was being done on it, and people were supposed to be fearful, but I noticed certain kind of data that didn't seem to reflect the kind of fear in financial markets that I would expect. So let me go into the introduction. The motivation for this paper is a natural experiment involving non-conventional monetary policy, as I've said here. Quantitative easing, its reliance on debt to smooth shocks from rare disasters. And part of the process, part of the modeling process, I extended the Mirror and Prescott consumption-based asset pricing, especially in light of a resurgence in the literature on rare disasters, some of which are listed here, particularly by Robert Barrow. He started that, and Jessica Wacker had important paper that's highly referenced. But there are also other papers that use natural experiments to evaluate the impact of quantitative easing, and one of the more famous one is by Gertler and Kiyotaki, and they use a DSGE model with financial intermediation and found that quantitative easing dampens the overall decline in output. A more recent paper by Penalava et al. Conducted a lab experiment in which a central bank buys bonds for cash in a QE operation, and they found that QE raises bond prices, etc. An interesting paper by Qi and Xiao, Cheng Xiao was an econometrician, actually a well-known econometrician, conducted an experiment with lockdown treatment for COVID-19 in Hubei province. And as we speak, as some of you know, China is reinstating another lockdown again. In a factor model with factor loadings, etc. So without further ado, I'll move my screen is frozen here. So excuse me a little bit. It's kind of slow. So the design of this natural experiment is as indicated. It follows, some principles by Mayer for conducting natural experiment. So what I did was I matched the Great Recession of 2008 and what is now being called, in some circles, the Great Lockdown of 2020. And I used the extended consumption capital asset pricing model to estimate an implied local loss aversion, and we found that match them on those dimensions. One of the other things, both periods, the Great Recession and the Great Lockdown, both of them were characterized by market crash. They had similar VIX scores, similar implied risk aversion response, similar yield curve patterns, and similar intertemporal marginal rate of substitution. However, the Great Lockdown of 2020 was motivated by an exogenous event, which is this COVID-19 pandemic. One could argue that the Great Recession of 2008 was comparatively endogenous. So what makes this a natural experiment then is the exogeneity of the Federal Reserve shock. We'll see, we could have, of course, a natural question is, hey, did the Federal Reserve do the same thing in 2008? And we'll see whether that's true or not in the upcoming slide. So the contribution of this paper basically goes to, the bullet points in red here, where I have pricing the Great Recession of 2008 in terms of M1SL. The cost during the entire recession period for the Great Recession of 2008 was roughly about 224 billion per month, whereas the cost during the QE sub-period is like 1.9 trillion. In case people, these numbers, even though I do mathematics, even I have a trouble grasping these things. A billion is 1,000 million, and a trillion is 1,000 billion. So, and so pricing the Great Lockdown of 2020 in terms of M1SL, the cost during the entire COVID-19 period was 2.3 trillion, and the cost during the QE sub period for that was 15.9 trillion. So let me reiterate this. There was a QE period, sub period in the Great Recession, and that cost about 1.9 trillion per month. I think the QE, the NBER recession date for the Great Recession of 2008 was like about maybe a little over a year, I think about 13 or 14 months. I know you could imagine the Great Lockdown for 2020, it was costing about 15.9 trillion per month. The pricing of credit spreads between, in comparing the two periods was really interesting. It was about 6 basis points during the Great Recession of 2008 for the quantitative easing sub period during that time. By the way, let me explain what I mean by quantitative easing sub period. We had the Great Recession as earmarked by NBER, and then we had a period inside of that where the Federal Reserve engaged in what one could characterize as quantitative easing activities. So that's what I mean by a sub period. It's nested inside the recession period. And when we fast forward to the Great Lockdown of 2020, we find that the average value for the credit spread was like 2.6 basis points. And for the QE period, the 2 basis point per month reduced the maximum by 1.5 basic points. And that kind of confirms Gertler and Kiyotaki experiment result. More contribution to the paper, the pricing of risk attitude, which is really why I wrote the paper. Implied loss aversion, I'm going to explain in a minute what loss aversion is. Implied loss aversion costs 22 billion per unit when the Great Lockdown period is excluded. Implied loss aversion jumped to 110 during the Great Recession. So the total cost was 2.42 trillion. Implied loss aversion costs 8.5 billion per unit when the Great Lockdown period is included. Implied loss aversion jumped to around 10 during the Great Lockdown. So the total cost was like about 88 billion. And I have here QE reduced the cost of fare due to implied loss aversion in the economy by 2.332 trillion compared to the Great Recession cost. For those people who may not be too familiar with behavioral economics, loss aversion is the idea that people respond asymmetrically to gains and losses. So, for example, if someone were to be given £1, there would be a certain amount of elation that's associated with that gain. But if that person was to lose £1, the folklore and the literature is that the person will have a visceral response that's at least twice as strong as the elation that they felt when they gained £1. So now I move on to pricing risk attitudes using the equity risk premium in the market. In other words, like the S&P 500, for example, minus the risk-free rate. For the Great Recession, the 2008 QE period, the average equity risk premium was about 2 basis points, and each unit increase in implied risk aversion index contributed 2 basis points. For the Great Lockdown QE period, the average equity risk premium was 6 basis points, which is interesting. And each unit increase in implied risk aversion contributed to 0.3 basis points. We'll see later on that in a sense, the Federal Reserve actually subsidized the market. And as we now know, some people got richer during the Great Lockdown. And we all know who some of these people are, mostly the super billionaires in the US. And the last 2 bullet points, I did some kind of robustness check by looking at the put right index risk premium, which showed that put writers are pessimistic during rare disasters and optimistic during quantitative easing. And we'll see how that is borne out in some regressions in a few more slides. And one of the other characteristics here is consumption beta is negative during rare disasters, but positive during quantitative easing. So let me kind of characterize, some behavioral decision theory and experiment. One of the seminal papers to estimate a normative range for risk attitudes. In other words, what you're looking at here is a paper by Holt and Lowry published in the American Economic Review in 2002. And what they did is they conducted an experiment using something called a multiple price list to elicit risk attitude for subjects in the experiment using a workhorse model, constant relative risk aversion. And what they found is that the spectrum for the distribution of risk attitudes is less than minus 0.95 for people who are highly risk loving. And it's up, when you get to like 1.37 for risk aversion, that is an unusually high number, and you should rarely ever see that number. So I just put this slide up here just so that people can see what the slight innovation I made is. I won't dwell too much on the theory. This is the standard toy model, standard 2-period model, contingent claims model. The difference between this standard, the CC CAP-M, and what you probably would see in the literature is I innovated the utility function. I used one of the what's called a value function actually in behavioral economics. The value function that is popularized by Kahneman and Tversky from an economist's point of view implies some kind of homogeneity, some kind of homothetic behavior. And that is an extremely strong assumption. So I decided to kind of relax that and just put, as you could see in the second to last line here, I put the lambda, which is the loss aversion index, as a random variable inside the utility function. Inside the utility function, inside the what the behavioral economists call a value function. And then that value function, I gave it a specification similar to the CRRA specification. And once I did that, I got a stochastic discount factor or pricing kernel that you're looking at the bottom of the page here, that M with superscript D, and that variable called var rho is like a subjective discount rate. Lambda is the implied loss aversion index, and that minus superscript, that's gamma, that is the implied risk aversion index. So it's a fairly simple pricing kernel, as it were. So let's look at some of the empirical results then, where I'm matching dimensions of rare disaster by eyeballing data. So what you're looking at here is a local implied loss aversion index in the macroeconomy. And what you're looking at here is a field of local loss aversion index. In other words, I have a formula that it's kind of a little bit involved to get into it now, but it comes out of a branch of mathematics called Lie group theory. Lie group is the infinitesimal calculus is for functions. Lie group is the equivalent for matrices. So what you do is you drop a little epsilon ball, as it were, at a local point, and you treat the center of that ball as a identity matrix, and the points that are away from that point, you treat them as another matrix, and then how far away they are is either singular or non-singular, and then you end up with this kind of structure where you could generate the set of all possible paths that the economy could take. So as you could see here, looking the two vertical line in the middle, where the curve tapered and got narrow, that was during the the Great Recession of 2008, but you will also see that there was a lot of background risk after the Great Recession of 2008 that lasted for almost 10 years, where that curve narrowed. When we fast forward to the right end of the curve, you'll see that the similar estimates for the Great Lockdown didn't last very long at all, and the economy started to come back together. By the way, just to interpret this curve, the parts on top of the curve represent people who are pessimists, and the part at the bottom of the curve represent people who are optimists. Difference of opinion is what leads to a trade. When the market crash, or using Akerlof's lemon market model, when pessimists and optimists agree, that's where you get that narrowing of the plot, and that signifies then that there's kind of fear in the market. Here's a more blown up picture of what happened during the Great Recession. As you can see, the period only lasted for about, compared to the 10-year period for the Great Recession, for the Great Lockdown, we had maybe about, given it at best 2 years, and you can see the market already started to come back out. Of course, we are back into a recession, but that's another story altogether. And here is a plot again that kind of shows a more visceral distribution of the shock in the financial markets. If we look at the rightmost tail, we'll see that when the financial markets crashed in 2008, the implied loss aversion index exploded to about 110. Now remember, according to the Nobel Prize winning work by Tversky and Kahneman, the median value of a loss aversion index is 2.25, right? But when the market crashed, it exploded to 110. Now, the purpose of putting this curve here is you'll notice in the leftmost corner, I have a vertical line. And what I'm showing is that using the median for a distribution can sometimes be misleading in terms of what else is going on in that distribution. So I was able to estimate the median value for the implied loss aversion index using Fred data, etc., as 2.22, which is pretty close to the estimate of 2.25 that Tversky and Kahneman found in their laboratory work. But the difference between me and them is when you go into laboratory university experiments with students, the range of your estimates tend to be really narrow. So basically, the experiments aren't capturing the type of visceral responses we see in the real world. And according to the experiments, whether you got divorced, whether you lose your house, whether you lose your job, your loss aversion index is going to be in a tight band. But of course, as we can see here, the underlying distribution here is really a Cauchy distribution, which admits any value greater than 0, including infinity. So here we look at the stochastic discount factor just to highlight the point I'm making. If you look at the left plot, and I'm looking for my thing here, I could kind of see if I could get the numbers right. That peak number is like about 55,000. Imagine that. In other words, and if you look at the bottom, the lines look really flat, right? But those lines are not flat. What happened is that during the Great Recession, there was such an explosion. It's literally like an atomic, like a nuclear weapon was exploded in the financial markets. What you're looking at on the right side is actually, the number was so big that I had to chop it off in order to get to see some of the other dynamics in the plot. So on the right-hand side, I so-called Windsorize it, remove the extreme values. And now you can see a pairing of the of the stochastic discount factor. The peak on the extreme right was where the stochastic discount factor exploded during the Great Lockdown, and the peak on the left is where the stochastic discount factor exploded during the Great Recession, minus, where that extreme value on the left was Windsorized. So if you look at the right plot, it looks as though both of those stochastic discount factor look almost, identical in terms of the explosiveness of what happened in financial markets. The time varying implied risk aversion, again, remember that according to Kenneth Arrow and according to the work by Holden Lowry, we should rarely ever see an implied risk aversion index greater than 1. But I'm sure if people who are familiar with consumption pricing, asset pricing model know that in the literature, it's not uncommon to see people calibrating models with values of 3, 7, 10, 15. I've seen one paper in the Journal of Finance speculated with a value of 250. Yet, in Kenneth Arrow's book in 1971, the well-known monograph, he said you should rarely ever see a number greater than 1. And true enough, my model is able to reproduce that those numbers similar to what they found in the lab. Why is that important? Well, it's important because one of the other puzzles in the literature is trying to find the intertemporal marginal rate of substitution. That is how people in the economy respond, when the Fed increase interest rates. If the model is estimated, since the intertemporal marginal rate of substitution for a CRRA specification is 1 over the implied risk aversion index. If your risk aversion index is greater than 1, what you're basically saying is the market is very insensitive to when the Federal Reserve increase interest rates. And we know that that is not the case in practice. Here, what we're looking at is yield curve dynamics. So I got 2 sets of yield curve dynamics. The one on the left is what the yield curve looked like. I plotted the yield curve going out at the maximum point at about 1,300 days prior to the, to the implosion of the market in the Great Recession. So I don't know if you can see those colors. We have purple, blue, different colors. We have 30 days prior, 90 days prior. So each of those curves have kind of given you the evolution of the yield curve. And as you know, when you have an inverted yield curve or a yield curve that's not convex upward, that's usually a sign of a great recession. Of a recession that is starting to take place. And you look on the right-hand side, we can see that leading up to the Great Lockdown, in other words, the economies of the world were poised to have, or at least in the U.S., was poised to have a great recession anyway. And, the COVID-19 pandemic kind of hid that and kind of masked that. So what we're looking at as I speak is what was hidden and camouflage during the Great Lockdown is now starting to come to fore. There's structural issues in the major industrialized economies of the world, and those things are probably going to be exacerbated by the failed sanctions that they put on Russia. But anyway, bottom line is yield curve dynamics, matching the curves on yield curve dynamics. We see that the yield curves were pathological in both periods. Now, this is the plot that kind of that puzzled me when I first did it. When I first did this plot, I did not have that black line in that black line you're seeing there. What happened is I plotted the implied loss aversion index, which I call a mimicking myopic loss aversion index, MMLA, and I noticed I use a rolling window. So what you'll find is that shaded region, which is the NBAR recession date, you'll find that while it is true that there was a jump during that period, you'll find that there was an even higher peak outside of the period. And that is an artifact of the econometric technique, where you kind of use like a 24 or 36-month rolling window. So, the full effect of the data is lagged, of the model is lagged. But if you look at the rightmost side of the plot, you'll notice that there's a thin shaded region in what the NBR recession date says the shortest recorded recession period in history. So you almost can't see that shaded region. But you notice that there's no jump. There's no jump in the MMLA index per se. In other words, it's capped by that green shaded line. And I was puzzled by that. I said, look, the amount of fear people had during COVID should be the same as they had during the Great Recession. Why am I not seeing that jump? And then something made me decide to just overlay the M1 or M1SL. I have M1 here, but that should be in the legend, that should be M1SL. And lo and behold, what happened is we can see the almost vertical jump. I mean, an explosive jump in the M1SL money supply. And what that signaled to me was that the money supply was aliasing for the fear that would normally be felt in the financial markets. In other words, the Federal Reserve in the US bought out the market fear by just printing money like it was going out of style. And that is what kind of, again, motivated this paper to find out what would the cost, what would the impact, what else was going on with what risk attitudes in the economy while we had this virtual risk substitution taking place. So again, to look at this in a different light, what we're looking at on the left plot is intolerance to decline in real disposable income. And on the right, I'm looking at intolerance to decline in real personal consumption expenditure. Now, those steps, that red line, that horizontal that looks like a step, what that is representing is, like Duesenberry's consumption ratchet on a paper written by Dybvig, who, as you know, was a recent Nobel Prize winner back in 1995, where he also looked at this consumption ratchet issue. The horizontal line is basically saying that once we have attained a certain standard of living, we have zero tolerance for that standard falling. So on the left-hand side, you look at real income falling wherever there's a gap. And when we go to the rightmost part of the curve, again, we're looking at the left half of the plot, I noticed that real income took a hit at the early stages of the Great Recession. By the way, that kind of lightly shaded gray area is signaling the full duration of the aftermath of the Great Lockdown. The kind of bluish area is the NBER recession date. But I noticed that soon after that, real income kind of went up slightly. And as you know, there was a lot of transfer payment made in the major industrialized economies of the world during the Great Recession. Now look at the rightmost curve. Look at how real consumption plunged. If you look at around the middle of the curve after the Great Recession of 2008, right? So a lot of people was kind of concerned about that. But if we look at the rightmost curve, there was a very, very short decline in consumption. But if we look at the plunge, it's actually deeper than what that plunge was during the Great Recession. But again, because of the tremendous amount of money printing and tremendous amount of transfer payments, we actually saw an increase in consumption, in real consumption expenditures, excluding excluding durables during that period. So again, this can't be sustained. We can't have a situation where we have an increase in real consumption, when people, when that is based on government transfer payment. So not surprisingly, many of the central banks of the world are now trying to walk back that largesse by increasing interest rates. So here, again, I told you about the time varying intertemporal rate of substitution. If we look on the left-hand side, the left-hand plot, you can see an explosion. That number that peaked up there is an explosion during the Great Recession. I think on the right-hand side, we see just before the US election in 2016 that Trump won, there was also a slight economic recession. And if you recall, for those of you who pay attention to American election, people blame Hillary Clinton for losing the election because she did not campaign in some of the so-called Rust Belt areas where there was high unemployment. Again, because of the explosive nature of what's happening on the left-hand plot, I Windsorized. Actually, I didn't Windorize it. On the right-hand side, I constructed a kernel density function. I look at the kurtosis of that kernel density function for values of the implied rate of a marginal rate of substitution. Remember, the numbers near zero means that the risk aversion index is relatively small, and of course, when you take the inverse of a small number, it gets really high. This is a puzzle that what's his name, Robert Hall has introduced way back, I think in 1978 or 1988, and that macrofinance people have been grappling with, trying to find a way to to get the implied marginal rate of substitution to be greater than 1, and that is another thing that my model is able to resolve. So let's look at time varying consumption beta using a 30-month rolling window. Again, if we look, consumption betas are negative during speculative regimes. So if I don't know if hopefully you can see this, just up until around 2010, where the number on the time varying CC CAPM under the window is less than that horizontal line. It's negative. And then just after the Great Recession, it went up and became positive. In other words, instead of speculating, people started to hedge. And if you look at the rightmost part of the plot, you'll notice that once again, just before the Great Lockdown, there was a lot of speculation in the market. Look at that plunge, just before 2020. Again, those numbers were so distorted by the explosive nature of the IMF implied marginal rate of substitution. By the consumption beta, sorry. What I had to do is Windsorize it so you can get a fuller picture on the right-hand side. So on the right-hand side, with the extremes removed, what you're basically seeing then is the consumption beta is actually negative leading up to the Great Recession. In other words, there was a lot of, which we now know, there's a lot of speculation going on in financial market. After that, people became very risk averse for almost 10 years after the Great Recession. Then they started speculating again just before the Great Lockdown. And of course, once the Great Lockdown hit, we see that the consumption beta started to rise again. And of course, it became positive in the extreme right portion of the curve. So let's look at the causal effect then. The causal effect is a simple econometric specification. It's estimated, as you can see there, the expected value, where dB is a dummy variable that takes the value 1 for quantitative easing dates. I didn't do a difference in difference because I didn't think it was warranted, but maybe I might do it. So look at the causal effect of quantitative easing on the implied risk aversion index. On the left-hand side, you see the causal effect of quantitative easing on the implied risk aversion index during the Great Recession. That left plot again represents the 10-year period. It's about 7 or 8 years, yes, almost 10 years in that gray area for how much what behavioral economists would call background risk that was going on in financial markets. People were still reeling from that Great Recession. Notice that the implied risk aversion number was negative just before the Great Recession. In other words, a negative implied risk aversion index implies risk seeking. So just before the financial market imploded, people was taking a lot of risk. Again, on the right side of the plot, we look at the causal effect of quantitative easing on implied risk aversion. Just before or soon after it was announced, we saw a lot of speculation in financial markets. Once people learned that the government was going to kind of subsidize the financial markets, but even then, risk aversion stepped in and it exploded back to to a high level, not as high as it was during the at its peak during the Great Recession. I think on my map it looks as though it was like about 1.5, and at its peak during the Great Lockdown, it was like at about 0.6. But nonetheless, we can see that the market responded, or at least people in the market responded in terms of risk attitude in slightly different ways for the causal effect of quantitative easing. Now let's look at the pricing of the implied risk aversion through the pricing of implied risk aversion via the equity risk premium. So the dependent variable here is the equity risk premium. Remember, the equity risk premium was estimated using a rolling window. And what you're looking at on the left-hand side there is just an intercept term, and the others are dummy variables. In other words, the IRA index QE08 is a dummy variable for the quantitative easing period for 2008. The IRA index for QE COVID is a similar thing. And by strict, there were two types of, by strict quantitative easing, what I meant was I went to the Federal Reserve website and got the narrow dates in which they defined quantitative easing. And then I created a dummy variable for that. The other IRA index for quantitative easing is just more generic. It has a wider band. But it was probably a date that macroeconomists, macrofinance people kind of speculated on. But the bottom line is when we look at the equity premium for the Great Recession of 2008, with respect to those implied risk aversion index. Sorry, wait a minute. Let me correct myself. I misspoke. The IRA index QE08 is the time series of implied risk aversion index during the quantitative easing period of 2008. So those are not dummy variables. I'm sorry. Those are actual numbers. And the GR 2008, however, for the equity premium is the window for the Great Recession of 2008. And the same thing, the Great Lockdown period for the COVID, GL COVID is, again, the NBER dates, the macroeconomist dates for the Great Lockdown. The strict GR08 is the dates published on the Federal Reserve website, which tend to be a narrower window, and the strict Great Lockdown COVID. So we'll notice then that the only time we found statistical significance was for the equity risk premium was during the strict great lockdown period. In other words, that's what prompted me early on in the early slides to say that the Federal Reserve was actually subsidizing the stock market for people who was invested in that. They got that largesse, for that risk premium. Here we see the causal effect of quantitative easing on risk aversion and equity premium. Again, the left-hand plot says causal effect of quantitative easing on implied risk aversion index during the Great Lockdown. I think we saw a similar plot before. Prior to the Great Lockdown period, we had some risk seeking in the early stages when the Federal Reserve announced that they were going to start printing money, and then shortly after that, the causal effect increased, as you can see by that jump. And on the right-hand side, the causal effect for quantitative easing on the equity premium. Now look how the equity premium jumped, how people were being rewarded for taking risk in the financial market. And then, of course, the equity premium fell shortly thereafter once quantitative easing came into full effect. So according to my notes here, the right plot shows that at the same time the market equity premium jumped, so it appears speculators were being compensated. And here I look at the quantitative easing, the effects of quantitative easing on fear of loss. So on the left-hand plot, again, the left-hand plot shows the causal effect of QE on loss aversion during the Great Recession of 2008. The loss aversion index dropped from around 17 to about 2.5 over that period. The estimated equation showed that the causal effect of QE was insignificant, however. However, on the right-hand plot, which has a strange, it doesn't mimic the left-hand plot. The right-hand plot shows that the effect of QE on fear of loss during the Great Lockdown. The loss aversion index dropped from about 3.5 to slightly less than 1. In other words, because of the tremendous amount of money printing during the Great Lockdown, we did not see the same kind of fear in the market that one would have expected compared to the Great Recession of 2008. And here, what I'm looking at is I use what do I have here? I think it's the dependent variable, it's the put right. No. The dependent, I have 1, 2, 3, 4, 5, 6 different regressions. So the topmost, so on the extreme left-hand side, what you're looking at is the so-called put right index, or the put right index premium relative to the 90-day US T-bill. It reflects put writers' optimism during quantitative easing and pessimism during rare disasters. And so for example, column number 1 is just a naive OLS. Column number 4 is where I, kind of use a new US robust test estimator because, just to kind of, because you probably know sometime when you make these robustness corrections, you get markedly different results. But you look at for the estimates of the beta coefficient were relatively similar, but we picked up statistical significance in column 4 for every dummy variable. So now the variables here, all the variables on the left are dummy variables. So for example, below I kind of define what they are. D911 is a dummy variable, equal to 1 during a September 2001 to August 2003. The dummy variable for .com, March 2000 to October 2002, and so on and so forth. The dummy variable for the COVID period is between March 2020 and December 2021, which is the end date in the data. And when we look at the implied risk aversion index, which is column number 3, we find that again, those numbers are the OLS consistent estimators, but on the rightmost, for inference purposes, we're looking at column number 6. And again, we are finding that that the implied risk aversion index was statistically significant during the COVID period, but it wasn't statistically significant during the Great Recession period. That is strange. You know, and I have to do some further analysis on that. And at that, the coefficient was negative on that, which means that at least for the D-COVID-19 period, that means that it's picking up some speculation. But for the DQE COVID period, it's picking up some hedging and risk-averse behavior, which is kind of what we would expect. And here is the pricing of rare disasters with the equity premium and credit spread. Again, ERP, equity risk premium, BAA, 10-year is the credit spread, typical macro credit spread variable. For us, the columns that matter, in other words, column 1 and 2 are OLS, but column 3 and 4 are with the robustness correction. One of the things that I found remarkable was that the coefficient seems to be almost like around 0.2. In other words, 2 basis points, regardless of whether or not, you know, what the rare disaster is in the market. So whether it's the dot-com bubble, Hurricane Katrina, the Great Recession, COVID-19, the QE period, the coefficient of those variables, at least the absolute value, is about 2 basis points. That is, I don't know why that is, but I sure would like to perhaps get some comments on why people may want to speculate on that. And here I kind of, what we're looking at here is pricing the rare disasters. In other words, in the left-hand column, we see the dummy variables again, but the lower last number, that MMLA index, is the time-varying loss aversion index in the market. The coefficients on that are in billions of dollars. There's no statistical significance on that. However, if we look at the DQE COVID period, we find 860 billion as the cost to the economy during that period. In other words, that's $15.8 trillion we are looking at. So those numbers, again, in columns 1 and 2 are OLS estimates. They are consistent estimators of the beta for the purpose of inference. However, we go on the right-hand side, but we notice that once the robustness check is done, that $15.8 trillion becomes statistically insignificant. However, the quantitative easing for the Great Recession of 2008 continues to be statistically significant. The same is true for Katrina, and the same is true for 9/11. So in conclusion then, the difference in risk attitude during the Great Recession of 2008 and the Great Lockdown of 2020 is the Federal Reserve M1SL response, which induced risk substitution by shifting risk to the Federal Reserve. Ergo, risk attitudes during rare disasters can be mitigated by M1SL. And the implied loss aversion index is the source of explosive fear in what I call a singular pricing kernel. Singular pricing kernel simply means that you can divide, you know, if lambda is a Cauchy distribution that admits any value greater than 0, then when you get if you divide 1 by a number extremely close to 0, it becomes very explosive. And of course, if you divide 1 by infinity, it becomes 0. So either of those extremes singular values, and that is why I use that. And here I just provide a representation theory for mathematicians, using something called an integral equation operator. So that is the end of the presentation, and I thank people for kind of listening through. Hopefully, probably getting the gist of some of the plots that I have. So if there are any comments or questions, please feel free to ask.
Yeah.
Here's some of the
Thank you very
literature.
much for the presentation. Well, I'm sure the mathematicians in our midst will understand every bit of it because I don't. Yeah, but that's excellent presentation and very interesting findings. I would want to throw the floor open. Let's hear comments, questions, feedback.
Let me see if I could get out of this mode.
Okay.
I'm going to get out of this mode so I could.
Yeah, but I think you should leave it on.
I want to get out of the full screen mode.
Yeah. Okay, so let me see if there is anything in the chat, and then if anyone is raising up their hand.
I don't see anything in the chat.
There's something from JDeep. He was asking if there are interactions with the dummy.
No, I did not. Because the dummy, there was, I did not interact the dummies because I wanted to separate, and I think that's a good question. I think he probably picked that up when I said that there was a strict QE period, and then there was a period that was a kind of, that was a greater window. Again, there were two sets of dates that I was using. The Federal Reserve had their own dates, which tended to be narrower than the NBER dates. So, of course, if I interacted them, I'll just be picking up, the Federal Reserve dates. Fortunately for me, it didn't introduce any kind of multicollinearity, at least not strong multicollinearity after I introduced the robustness estimator.
Yeah. Does that answer your question, JD?
Yeah, I mean, partly. So I now I understand that those regressions were like just subsample regressions. Basically, you're trying to regress these IRA measures on the regress the equity risk premium or the IRA on the on the different measures of the IRA. Yeah. So I was kind of wondering why you didn't do like a whole sample regression, like just have dummies instead. So I was just curious why you chose to do these subsamples, especially given you said that there was like a moving average situation anyway.
Window. I was using a window.
Yeah, because you're using a moving. Yeah, exactly. You're using a rolling window, and so therefore the estimates that you're running in the subsample regression are anyway not like really contemporaneous as such. So it's probably not necessarily giving you the kind of numbers that you're looking for. Maybe it's causing some of the problems that you found, like the sort of the flipping of the signs and a few of the other issues. So it's just something worth checking is whether these regressions are like,
right.
Yeah.
Right. That.
Yeah, thank you very much, JD, and thanks, Charles, for clarifying that. Are there anyone raising up their hands or nothing more in the chat box?
I don't see anybody.
If there's no other question, then maybe I'll ask a couple of other questions if that's okay. So
yeah, that's fine.
Yeah, so I'm just trying to think about the core of what you've done. So there's when you highlighted your conclusions and your contributions, there were a lot of different sort of numbers that were coming out, and so I was a bit confused by sort of terminology like using the cost of M1SL. So I mean, what exactly is the cost in terms of M1SL. So what we mean by that is the increase in the money, sort of liquid money supply.
No, no. What I
Basically,
did, yeah, no. What I did is
so
I used M1SL as a dependent variable,
okay,
and then as my regressors, I used the dummy variables for uh, the rare disaster periods, as dated by NBER and rare disaster websites, to see how much over the period of those dummies, so to speak, the dummy being equal 1, what was the coefficient? And the coefficient then would be the cost, how much M1SL on average. That's what I was calling cost. Maybe that's
okay.
probably not the right word, but
Yeah, I think that
yeah.
kind of confuses the interpretation a little bit. So maybe better do you avoid using the cost, because essentially it's difficult to think that M1SL, a change in M1SL is a cost. Like
Mm.
it's probably like, I mean, I don't know what it is exactly, because I'm not really good at this monetary sort of interpretation. But from what I can understand, it's just basically what you're saying is that in a way, monetary policy is kind of working, in the right way. It's increasing. You're increasing sort of this money supply, although that's not what the Fed targets, right? It's the Fed works with interest rates. So only the quantitative easing can do something like what they've done here, or otherwise through some kind of government borrowing and subsequent fiscal policy kind of action, can you increase this kind of M1SL, right? And so I was a bit I was just thinking that there may be a cost to it, but what is the cost? Maybe the cost is in terms of inflation or something else.
Oh,
But
you're
just
looking at it. Oh, I see what you're saying. You're looking at it from from an economist
Yeah.
point of view per se. That's how an economist would perceive cost. And I was looking at it. Look, these guys printed trillions of dollars, and they've been printing them, over the last for the duration of the sample. Let me see how much money, the average amount of money, for example, that was printed, and maybe that is perhaps a more accurate description as opposed to saying cost, like I did. What was the average amount of money printed during various market disasters,
yeah,
whether
and
it's September 11, whether it's Great Recession 2008, or whether, as we now know, the Great Lockdown?
yeah, and that sounds like an interesting sort of uh, uh, quantification in itself, but and also the fact that in fact, for me, the one of the conclusions I found from your from your results is that, in fact, they needed to sort of really flood the market if they wanted to reduce the equity risk premium, right? So the effective or implied equity risk premium, they really needed to increase M1SL very, very significantly, which is what they did during the COVID period. Oh, and
Right.
so
And yeah.
and so the question then is whether that, I mean, I think that's a question that you don't necessarily, you're not necessarily interested in answering, is whether that has future implications, I suppose, which we kind of all know that it does, right? So it's fine that they reduced the equity risk premium at the time from what it could have been or would have been,
Mm.
but we don't know what it's going to have, what is going to be the impact of that in the future. So for example, the kind of inflation shocks and other things that are coming subsequently as a result of it. Or as you said, I think you used the words that they kind of covered up all everything that was systematically problematic in the economies, and now,
Right. They use risk substitution. What
yeah,
they did, that's a fancy word. They
yeah,
printed money and bought out the risk to quell financial markets.
yeah,
And during that time, of course, certain people like Jeff Bezos and other people saw their wealth explode, to ridiculous levels. But because of the structural issues in the economy that existed in the uh, advanced economies that existed before COVID-19. In other words, COVID-19 really hid a lot of structural issues. I have a different model that in 2018 I predicted there was going to be a recession. I'm on record doing that on tape, so nobody can tell me, it's after the effect. And I said that's the only reason that they probably get rid of Trump, in 2020. But It turns out that COVID-19 came. But what we are seeing is another set of forecasts where, many macro finance people believe there will be a recession next year, 2023. And a lot of, in fact, some people believe we're in the early stages of a recession anyway. So despite all that the Feds have done during the great lockdown, they're still unable to, to stop recession, and we're probably back in the world of Minsky, where financial markets just kind of have this kind of destruction and creative things that they do.
Yeah.
Okay, so yeah, that seems to make like that seems to be like a more direct message than so the risk substitution element seems to be the uh, kind of a more clear sort of thing that you can quantify, I think, and it's quite interesting as well.
Yeah.
Yeah.
Thanks very much, JD. While waiting for more hands, I'm also interested in I was just curious to know how, I saw in some of your models, I saw that you model fear of loss. So I was just wondering how fear was measured.
Oh, that's an excellent question. As you probably are you familiar with behavioral economics at all? Some of the stuff like loss aversion.
No, not really. I'm an
Yeah, okay.
accountant.
No, that's fine. One of the um, risk attitudes that has been introduced in economics and psychology, particularly coming out of psychology, is the notion that, like I said earlier, like I started off saying, is that people feel a certain amount of elation if they won a 1 pound, for example.
Mhm.
But if they lose 1 pound, their visceral response, they have a strong negative response that almost is twice as large, in fact, over twice as large as the elation that they would feel for winning. In other words, there's a tremendous amount of fear for losing.
Yeah.
And that causes asymmetry, in terms of response. Now, it turns out that loss aversion is also intimately related to risk aversion,
Yeah.
but in ways that are not sometimes always clear in classical, because loss aversion is a concept from behavioral economics.
Mhm.
If you're familiar, you won't ever see it in a classical, neoclassical type setting. So, what in a paper I published in Journal of Economic Behavior and Organization and Journal of Mathematical Economics, I prove theoretically that the loss aversion index is actually a member of a generalized Cauchy distribution. One of the characteristics of a Cauchy distribution is that only the median exists. A Cauchy distribution admits infinity as a legitimate value. So it can take a value anywhere from 0 to infinity.
Okay.
So to estimate fear in the market, then we estimate loss aversion. How loss aversion? Then people have a certain amount of fear of losing. That visceral response that I told you about.
Okay.
Okay, and part of the technique I use to do that, as opposed to something more sophisticated like a Kalman filter, which would just I don't know if I didn't think it would buy me anything different. Was to get this kind of rolling window for 24 months, 30 months. There's only I could only go so low, before the data allowed me. So I went as low as possible. I think the lowest window I used was 30 months.
Okay.
Kind of rolling window to get the sample going. And we would find, like, during the Great Recession of 2008, as we expected, there was tremendous amount of fear. And if you recall, in one of the plots that I showed you, what they call the stochastic discount factor, it exploded to over 50,000.
Yeah, that was what I was
Yeah, I
wondering.
mean, it's
How
really
it was
like a
measured.
nuclear explosion in the financial market. That is
Yeah.
that is not a simulation. That is real market data. In fact, and it made everything else throughout, in the history of financial market looks relatively flat. So I had to remove that number, Windsor horizon as it were, so you could actually see, fear at other points in the market. And what I was hoping, part of what motivated this research is I expected to see a similar explosion during the great lockdown, and I didn't see it.
Yeah.
And I wanted to know why, because it seems to me people were, at least where I know, a lot of people was fearful about COVID. Nobody knew what it was. And the markets literally shut down, but I wasn't seeing that explosion. And I wondered why. And it turns out that the reason why I didn't see it is because the Federal Reserve printed a whole lot of money. Now, they may have learned from the Great Recession. If you notice in one of the other plots, I showed that even after the NBER recession dates ended around 2009, there was a lot of what's called background risk in financial markets. For about 10 years, people were scared to take, a whole lot of risk in financial market. There was a lot of conservative investments. Again, I would have expected coming out of the pandemic to see a similar set of behavior, but I didn't see that at all.
Absolutely. Yeah. Yeah. I guess the pandemic was more of people were more concerned with life threats.
Right. So the pandemic was from what economists would call an exogenous event.
Yeah.
The Great Recession of 2008, as you probably know, was triggered, depending on who you talk to, by issues going on with the mortgage industry. And believe it or not, as we speak, I was reading a couple of days ago where the U.S. government is again decided to subsidize mortgages for over $1 million US. So people who have mortgages for over $1 million US for their property and home, the Federal Reserve, the U.S. government is going to do the same thing that it was doing prior to the 2008 Great Recession. It's unbelievable.
Well, so thank you so much for clarifying that. I think I can see. Oh, JDP has something to say again. All right, JDP.
Can you hear me?
Yeah,
Okay. Yeah. Sorry, I don't want to sort of monopolize the conversation, but I just had one other comment that I wanted to make, which was the whole point about talking about causality and the experiment. I mean, I didn't really get that from your presentation, and based on what you've just said, it doesn't seem to me that it was necessary to think of it in that way, because you talk about matching the two events and thinking of one as a natural experiment, but I mean, I didn't see any of the results which suggested that you were treating them as as experiments, in the sense that there was no, like you said yourself, you didn't do a difference in difference or any other such kind of analysis where it was important. So, I mean, to me, it seems that like the big contribution is this incorporation in the in your Euler equation, etc., of this lambda and so on, and so you've got this whole so that seems to be the sort of the analytical contribution. So I don't see the point, like maybe it might be helpful for a paper to like not think of it as an experiment compared to one event, comparing one event to another in the same way that you've just said. I mean, it's a nice thought, but maybe if you wanted to call it that, you would have to do a lot more work. It seems to me that the work you've done is enough to sort of communicate some sort of conclusions without having to call it an experiment. It's just a suggestion.
That is why, again, like I said, I call it that. That's what the papers, in the literature review called it. And basically, we're looking at treatment. In other words, the Federal Reserve, I used the Great Recession of 2008 as, say, the benchmark, right? There are certain behaviors that, in terms of risk attitude, certain behavior in terms of Federal Reserve. In other words, there was not as much quantitative easing during 2008 relative to 2020. So I figure, let's look at that as a control period. A great something happened in the financial market in 2008. The Federal Reserve, stayed comparatively flat-footed, and then up comes this exogenous event in 2020, And then they have a treatment. You know, they kind of, you know, flooded the market with a printing press. You know, so that is how I figured, comparing two cataclysmic events in the market. Why did the Federal Reserve respond to one event in a way that they did not respond in the other so-called similarly situated event? Now, you're right. I'm not in a laboratory, so you know, so I have to take poetic license. So I kind of look at behavior of, you know, certain benchmarks, the yield curve that kind of signals when a market's going to be in recession. You know, whether it's a year before, 2 years before. I say, okay, let's look at some of the other thing. What was risk attitudes in the economy? Was all these other kind of risk-related benchmarks? Compare them, try to match them with plots. But if, to take your point to its logical conclusion, remember that I cheated a little bit in that I Windsorized extreme values from 2008. And once I Windsorized them, I was able to get these kind of eyeballing the data, you know, where I saw the match. So if you take out, because, you know, what happened in 2008 was endogenous. One could argue whether, in fact, um, it should even be compared to, you know, the Great Recession of, the Great Lockdown of 2020.
Yeah, and plus there were lots of widespread fiscal transfers, which were quite a big factor. So
Excuse
uh,
me?
a lot of widespread fiscal transfers. So essentially, people
Yes.
getting money for not doing anything and sitting at home. So
Yeah.
that was a different feature as well. So that
Yeah,
doesn't.
but
Yeah.
you know, the thing I was concerned about, and I don't know how much literature you recall that after the 2008, there was a structural shift in the developed economies where that never came back. There was so-called hysteresis. A lot of people lost money in their pensions. You know, a lot of people who were planning to retire couldn't retire, and that had a reverberant effect for over 10 years. And remember, one of the hypotheses is people have an intolerance to a decline in standard of living. So I think the Federal Reserve in the U.S. might have been, again, I don't know, I may have been trying to avoid another kind of situation like that, and they decided, you know what, we don't want to have another 10-year. We don't want to have some more hysteresis here. Let's open the printing press. Again, this is pure speculation on my part. I don't know. I haven't read that anywhere.
Mm. All right. Thank you very much. Any more comments from JD for anyone else? Let's see.
I don't
Nothing
see
in
any
the
more
chat.
comments. I think people are probably ready to go home.
No, I think it's more of the mathematical models.
Actually, I didn't show. I didn't. I actually toned down the math a lot. Well, at least from my perspective, you know, I just came back from something at the Isaac Newton Institute for Mathematical Sciences at Cambridge University, and you know, there we had people from industry who were kind of familiar with the mathematics. So it's, you know, I sometimes have to
Mm.
realize the audience, the target audience. I'm
Yeah,
mostly
that
used to
that would be
talking to
very
people
engaging.
who.
Yeah. Okay. In the absence of any more comments and feedback, we just want to say a big thank you to Charles-Cadogan for honoring our invitation and for such a brilliant paper presentation. Let's give him a round of applause. If yeah, and I think with that, we want to bring the session to a close. Thanks
Yes.
to everyone for attending
And I
today.
thank everyone for suffering through the presentation.
Yeah. And on behalf of Victor, I want to apologize for his absence, which, I mean, he would normally prefer to, you know, chair such, an interesting paper session like this, especially because with relevance to finance and the markets. Yeah, but he is unavoidably absent today. So on his behalf, I want to thank everyone for being present today to listen. And thank you, JD, for making it an interactive session as well. All right. Thank you. And bye, everyone. Thanks
Bye-bye.
once again.